The next topic we're going to take up is a very important one, and we're just going to get a start on it in this set of lectures. We're going to talk about proofs. And what I'm giving you here is a sample whose details you don't need to worry about. This is the kind of thing that proofs look like. They have numbered sequences of well-formed formulas. Over here you have information about what's going on. In this case, we've got three premises indicated by PR, a therefore, and then what we're trying to prove. And then each further step is justified by citing a rule and citing what line or lines it applies to. You do not need to be able to make sense of this proof right now. This is simply an example of what proofs look like. But before we can even get to proofs, we have to have some more basic tools. We need to have some rules of inference of the sorts that go into this proof. And so those are the things we're going to start mastering here. Well, rules of inference, you might think that they're determined by what things mean, by how we understand how certain inferences work. And it's not as though that's a bad idea. It's that it doesn't quite fit with the point of proofs in formal logic. In formal logic, we make a very strict separation between issues about truth and meaning and issues about form and grammar and syntax. The rules of proof are strictly defined in terms of form, grammar, and syntax. A blind, dumb machine that's keyed in the right way can tell whether something is a legitimate step in a proof simply by looking at its grammatical form. And then later on, there are questions about how form and content fit together. But we start out with the strict separation, and that's going to come up here. These rules of proof are defined strictly formally, and we will explain as we go along what that means. The upshot is that it makes it completely unambiguous when we actually have a proof. Our first rule is really simple. It's called double negation. We simply write DN in proofs. And it's got two versions. If you have a woof that is double negated by the rule DN, you can drop the double negative. Likewise, if you have a simple woof or a complex woof, doesn't matter, so long as it's a woof, you can double negate the woof. Notice I'm using boldface here. This means that these aren't just sentence letters, they represent any woofs whatsoever. So that's what the rule means. The rule does not apply within well-formed formulas. You can't take a complex well-formed formula and go inside it and apply double negation to some part. It's not that that would be incorrect reasoning, it's that it isn't an example of this rule as it's grammatically, syntactically defined. More about this later. So here are some examples. We've got this rather complex formula here that was double negated. We drop the double negative. This follows by dn. Here we've got a formula that we put in brackets and double negate. Once again, that's a case of the rule dn. These are not examples. The problem here is that this woof is not double negated. It's the negation of a conditional. We have a bracket between these two tildes, and so this is not an example of dn at all. This is an example of the point about not applying rules inside woofs. From A and not B, it follows that A and B. That's actually correct, but it doesn't follow simply by the rule double negation. Double negation applies at the level of whole woofs. We don't apply it inside. So the first is simply invalid, as it turns out. The second is valid, but not an example of the rule. For conjunction, for and sentences, we have two straightforward rules. The first one says if I have an and sentence, I can extract either part. I can extract the x here, or I can extract the y. The rule is called simplification. We just call it S in proofs. The second rule is for building up conjunctions. If I have two woofs, I can put them together with and in either order. That's an example of the rule called conjunction. So that's what the rules are. Once again, we don't apply these rules inside sentences. They apply at the level of whole sentences. And here are some examples. From P or Q and R, we can get the more complex sentence R and bracket P or Q. Notice we can combine these with and in either order. Here we have P or Q and R. We can simplify it and get R. We could have simplified it and gotten P or Q. Either would be correct. This is not an example. P and Q or R, therefore P or R. Well, the trouble is that we tried to apply simplification inside a complex woof. We are not allowed to do that. That's not an example of the rule of conjunction. Likewise here, we have P, we have Q arrow R. We tried to take the Q by itself and then the P and then combine them using the rule of conjunction, but that in fact is not an example of the rule. For disjunction, we have two rules, one of which you'll find a little peculiar, but it really is a rule, and you really do need to know it. The first rule is disjunctive syllogism. If I have x or y, and I can eliminate one part, either the x, by knowing that it's not true, or the y, by knowing that it's not true, I can infer the other part. But the grammar matters. Here we have x or y. Here we have one of the disjuncts plus an extra tilde. That's the form of the rule. And then we can infer the other disjunct. Likewise here, one of the disjuncts plus an extra tilde. We can infer the other disjunct. That really does matter. The rule of addition is the odd one here. From x, I can infer x or y, where y is anything you like. Likewise, from x, I could infer y or x, where again, y can be anything you like. This seems odd. It may even seem somehow logically offensive, but it's correct. An or statement, as we understand it, says that at least one of its parts is true. That's when an or statement is true. Well, if x is true, then at least one part of this woof is true. Likewise, if x is true, at least one part of this woof is true. This is a rule that grates on the nerves, but it is a perfectly correct rule, and you need to get used to it early. So disjunctive syllogism, or DS, a straightforward rule. Addition, a peculiar but correct rule. Disjunctive syllogism is sometimes called argument by elimination because we've got an or, we eliminate one part, and we're left with the other. And likewise, to comment on addition, it really is peculiar, but it's valid. Here are some examples. Okay, here we have not R, we have P arrow Q or R, and then by disjunctive syllogism, we can infer P or Q. We had an or statement. We had one of its parts plus an extra tilde, and we could infer the other part. This is an example of addition. We have P, and we can tack on this monstrous ugly formula here, although, pardon me, I left off the extra curly bracket on the end. This seems odd. You might wonder why anyone would do it, but it's correct. These are not examples. This one looks like it should be fine. P or not Q, Q, therefore not P. You think, well, we've eliminated not Q. Semantically, in terms of truth and meaning, yes, we have. In terms of the syntax or grammar of the rule, we don't have an example. Because we don't have the disjunction and another premise consisting of one disjunct plus an extra tilde. We have one of the disjuncts minus a tilde, and that's not the form of the rule. So this is not an example, even though it's valid. Likewise, this is not an example of the rule of addition. We have P and Q, and then what happened is this was a case of taking the P by itself and trying to apply addition to it. The rule of addition applies to whole woofs. If we have a whole woof, we can add on another woof with an or, but otherwise we're stuck. Okay, this is a basic set of rules for the connectives that sort of matter the most, or that we use most often before we get to conditionals. Conditionals are going to involve some special considerations. What we're going to do next is we're going to pause here. We're going to go on and look at the basic rules for conditionals and postpone until later some other rules about conditionals. And then we'll look at some further rules for biconditionals and a mixed rule. But in the meantime, we're going to pause here This will be part one of this lecture on proofs. You should listen to and pay attention to both parts.